Uartek Rover team was founded on January 1st, 2023 in Manisa Celal University and joined its first competition ERC'25 in last year. Despite limited resources, we gained valuable experience in our debut session, but more importantly, we learned a lot from our mistake. This year, we are back stronger and more focused. We've made changes inside the team and how we operate, all to achieve better performance and aim higher. Our core team is made up of mechatronics and one software engineering student. We all get involved in every part of the process, from coding to mechanical design, electronics to science. And here how we organize at Uartek. Mechanical and assembly takes care of the rover's movement and chassis design. Electronics handles PCBs, power distribution and wiring. Computer science runs the software, autonomy and communication. And science dives deep into geology and planetary analysis. So what drives us? Not the gears and the wires, but the thrills of the exploration. We believe in future of multiplanetary missions, so we want to be part of it. That's why we joined European Rover Challenge, not just to compete, but to learn, to grow, to prove that even with limited resources, our engineering can shine on the global stage. So buckle up, because this is more than just a robot. This is Barkan V2 and he is ready to make some history. Over the past year, we have made significant improvement to our rover Barkan, focusing on both mechanical durability and system integration. The rocker bogie suspension has been optimized for better traction and incline handling. The fixed part of the rotating joint was reinforced using M20 threaded rod. By moving the differential bar lower, we improved the rover's balance and make it more stable and uneven ground. We are currently developing a science module capable of deep soil sampling, reaching depths of to 13 centimeters. The mechanism moves along linear system, enabling precise vertical penetration into the ground. It is designed to collect both surface, regolith and deeper soil layers, allowing for a more comprehensive understanding of the terrain. Each collected sample will be individually weighed and stored, enabling us to analyze differences in mass and composition. This system is currently in the assembly phase, and we are actively refining its structure for reliable integration onto the rover.
Our rover is developed on ROS2 Humble and utilizes the Kinect V2 sensor. SLAM is implemented using RTAB map. Sensor fusion merges IMU and visual odometry data to maintain a reliable localization. Navigation runs through the Nav2 stack for global path planning and local obstacle avoidance, using the synchronous map and sensor input. We extract 2D laser scan data from Kinect using depth image to laser scan and combine it with a physical wide LiDAR JSIG. Comparing both sources improves depth accuracy and obstacle detection. We use arco markers and evaluate for object detection. Recognized objects are logged as semantic markers in the map, enabling future decision making based on visual cues. Kinect is integrated using open source Kinect 2 ROS2 package, which publishes color, depth and point cloud data compatible with ROS2.
To test and validate our systems before deployment, we built a full URDF-based module of the rover and integrated in the gazebo for physics-based simulation. This environment allows us to run software-in-the-loop tests, refine autonomous behaviors, and train operators using realistic mission scenarios. Additionally, we use RViz2 for visualization of sensor data, including point clouds, transformation frames, and navigation paths. This comprehensive simulation and interface pipeline ensures that our development and testing cycles are fast, safe, and accurate.
We have designed and built our own custom quadcopter. It's featuring a lightweight carbon fiber tube and reinforced 3D printed parts. It automatically takes off from the rover, follow up the paths, capture high-resolution imagery of the terrain, and skate targets. Thanks to its durable airframe, it can safely handle harsh conditions and minor collisions. Controlled by Pixark and Raspberry Pi. The drone supports both manual and autonomous missions. Its software is designed with multiple failsafes, including emergency return to home, geofencing to prevent unauthorized flight zones, and real-time system health monitoring to detect critical failures and trigger safe landing protocols. Robust data encryption is used during communication to ensure secure control signals and data integrity, even in remote environments. After completing its task, automatically lands back on the zone, ready for redeployment.
Our robotic arm is fully integrated into Rover's autonomous system and used for tasks such as manipulation, environmental interaction, and soil sampling. It has 6 degrees of freedom. The shoulder pan and lift joints use high torque servos with gear reductions, enabling 270 and 90 degrees of motion, respectively. The elbow joint is powered by a NEMA 23 stepper motor with a 5-to-1 gearing. Torque is transferred via 25/8 chain from the base to reduce the load on the shoulder joints. The wrist joints and end effector use 25 kg servos for precise 270-degree motion, and the arm can autonomously swap tool heads using 2 25 kg electromagnets. It is designed to be modular and repairable. Bearings between joints reduce friction and increase stability. The structure is built from carbon fiber tubes and PLA plus parts for strength and lightness. Smooth movement is achieved using ramp library, which ensures gradual acceleration and precise control. Joint commands are calculated in ROS2 and executed via an ASP32 controller.
The project initially with collecting a dataset, led by our computer science team. We gathered object images from various sources, and each one was carefully marked and labeled, a critical step in training the model properly. Accurate labeling significantly improved the learning efficiency of our object detection algorithm. Once the dataset was ready, we began training the model using Python-based libraries. During training, we fine-tuned hyperparameters to achieve optimal performance. We used YOLO V8 for object detection, which allow us to identify objects, retrieve their labels, and extract pixel coordinates in real time. With this information, we can accurately locate each object and send its position to the robotic arm for further interaction.
This year, Uartek Rover team chose Jezero once again as the basis for our research, to highlight the significance of Lake Selda and explore one of Earth's best analogs for Martian environments. To study our samples, we developed a custom-built microvolume spectrum analyzer. With it, we can examine chemical composition, purity, protein levels, nucleic acid content, and fluorescence properties in great detail. Fluorescence helps us understand mineral density and any potential organic metal interactions in the soil. By analyzing nucleic acids, we'll gain insight into microbial diversity, biological activity, and soil fertility. We are also using NPK sensors to measure key nutrients like nitrogen, phosphorus, and potassium, essential indicators of the region's potential to support life. These geological features point to the possible presence of water in the past, and where there was water, there might have been life. If confirmed, this could have been an environment suitable for microbial organisms. Monitoring environmental conditions is just as important. Using your sensor array, we'll continuously track pressure, temperature, and humidity, both for scientific reliability and support drone operations in the field. This will help us maintain ideal testing conditions and keep the entire mission running smoothly. Soil pH levels affect plant nutrient uptake, so we will also conduct experiments to determine the pH level. By comparing Earth's geobiochemical process with those of other planets, we hope to contribute to ongoing search for habitable environments beyond our world.